So this video is introduction to heat transfer, which is represented by the symbol Q. Q, I don't know how they came up with Q, but Q is an equation. So on the equation sheet for the AP test, Q is equal to M times C times delta T. What does this all mean? So M is mass, C is the specific heat capacity, okay, and then delta T is the change in temperature. So it's always the final temperature minus initial temperature. We learned last video that the specific heat capacity is, well, if it's specific, that means it's by mass. So usually that is in units of joules, and then per grams degrees Celsius, okay? That means it takes that many joules to heat up 1 gram of that substance by 1 degree Celsius. So mass has to match these units. And if it's grams here, then mass has to be in grams, okay? If you have a mass that's different than this unit here, then you have to make sure these two are lined up. And then temperature is in Celsius, but it's a change in temperature. So if you have a change in temperature, let's say I have, I go from a temperature of 50 degrees Celsius to 100 degrees Celsius. Okay, so my delta T is, if I subtract these two, it ends up being 50 degrees Celsius, this change in temperature. Well, if this was in Kelvin, it would be, so 373 Kelvin minus 323 Kelvin. And that change in temperature is still 50 Kelvin. So it doesn't really matter what temperature scale you use, as long as if it's Celsius or Kelvin, that change in temperature is what we're looking for. And that's what Q is it's always, you're always heating up something or cooling down something. It's not a specific, it's not a temperature. You can't have heat transfer if something is at the same temperature. So Q, you always have to have a change in temperature. So you always need a change in temperature, delta T. This unit overall, when I multiply everything out, grams cancels out, Celsius cancels out, and you end up with joules. So J is joules. That is the standard SI unit for energy or heat. So let's try this. I have a sample of water. Let's say I have a mass of water is 27.41 grams, and I have specific heat capacity of water is 4.18 joules per grams degrees Celsius, or 4.18 joules grams degrees Celsius. There, calculate the quantity of heat going into that water. So all I need to do is just take Q equals M times C times delta T. So my M is 27.41 grams. C is this number here, so 4.18 joules grams degrees Celsius. Grams are going to cancel out. And then my delta T is my change in temperature. So it's 22.9 minus 20.0. Okay, so this ends up being 2.9 degrees Celsius. So I just take that, multiply it together. Let me get a calculator real quick. So I multiply this out, 27.41 times 4.18 times 2.9, and that ends up being 332.3, and my units for that end up being joules. So now this is energy going into the water. If it's cooling down, that means energy is exiting the water, and that would be a negative number. So Q does have direction. If if Q is positive, that means energy is going into that thing. So energy goes in, and then if it's negative, energy is coming out. So if it's negative, energy leaves. And we kind of saw this last year when we had endothermic or exothermic processes. If it's endo, that means it's going in, exo is going out. Okay, so what if we do the other way around? What if we have an object, let's say an object takes 450 joules to heat up, temperature rises 3.1 degrees, the mass is 297 grams, what's the specific heat capacity for this object? So now we have, same thing, we have, this is Q, so I'm gonna write this down, this is Q. This is my change in temperature. My delta T is my change in temperature. This is my mass. So Q equals M times C times delta T. My 450 joules is equal to 297 times C times delta T is 3.1. Okay, I want to solve for C. So to do this, I gotta multiply these things out first. So 297 times 3.1. We're basically doing algebra here. So this is 920.7 times C equals 450. And now to get C, what I gotta do, I gotta divide both sides by this number to get C by itself. So 920.7, divide this out, 450 divided by my favorite button is the answer button, and it's 0.48876 or 0.489. So my C equals 0.489, and my units for this, I just, you got all these units up here, but if you know the units for heat capacity, you're gonna have joules, and it's got grams here, so grams, degrees Celsius. Okay, so you gotta make sure you have all your units for whatever we're doing here. So that's one of the problems in your assignment is like that. Okay, so now how do we use this in any kind of experiments? Well, the first law of thermodynamics is the thing that we use the most in something called calorimetry. First law says energy cannot be created or destroyed. So let's say I have 2 beakers of water. I have hot water, 50 grams of this, which is 90 degrees Celsius. Cold water, 25 grams, 20 degrees Celsius. And I mix the two together, okay? You could calculate this using the techniques I have. I calculated it for you. The final temperature ends up being 66.7 degrees. But the big idea is this. Well, how can I make these calculations? So if I mix two things together, we'll have a Q of hot water, okay? So that's my energy that the hot water is losing. I also have Q of cold water. So everything that I'm dealing with has a Q. As I mix these together, you're inevitably gonna lose some energy to the environment. So it's gonna be Q environment. Okay. And so when you mix things together, you have these Qs, and the first law says that if I take all these things and taking them into account, it all equals 0. Because there's no change, there's no energy lost, there's no energy gained. We don't create or destroy energy, it's always there. In this class and in most chemistry situations, we try to get rid of this, okay? So this thing here, because we don't want to deal with the energy from the environment, we typically use insulated containers. So if I insulate the container really well, if I put styrofoam or something like that, and I try to eliminate the energy lost to the environment, then I am making a closed system. And so when I can mix these things together and I can calculate things, then all I have to worry about is this stuff right here. And then I can make calculations dealing with, oh, I got hot water, I got cold water, I can calculate some numbers using that. So that's kind of the big idea for using calorimetry experiments. And so in the lab that we're gonna do when I get back is we're gonna take a piece of hot metal. I'm gonna have you watch another video. The hot metal is gonna go into cold water. So this hot metal is gonna be at a temperature of about 100 degrees Celsius. This cold water is going to be something that you're measuring, and we're going to not know anything about this metal, but the metal is, every metal has a specific heat capacity, and if we know lots of stuff about water, we know some stuff about the metal, and we mix the two things together, well, what's going to happen to the water? The temperature is going to go up. What's going to happen to the metal? Sorry, the metal, the temperature is going to go down. And when I mix them together, I can figure out the energy transfer. And so what ends up happening is we have a cube of metal, we have a cube of water, and we have a cube of environment, right? But the environment, we want to get rid of this. And what is that all equal to? 0. So that's how we use Q equation and heat transfer to do basic calorimetry.